Assalamu alaikum students. Welcome to another lecture of Slates. This is me, Khawaja Yasin. Let's study chemistry. Students, when we talk about A-levels chemistry and especially AS chemistry, there is one topic which mostly confuses the students. Then that is the shape of molecules. You know, when shape of molecules is concerned, there are various geometries, various angles, and various bonds that you need to understand. So in this topic, we will be covering all the shapes that can be there in your exam. There are more shapes otherwise in chemistry, but in A-levels, we have a restricted syllabus. So, in order to understand the shapes of molecules, the electronic configuration is very important. You need to know well about how to make electrons, how to make lone pairs, how to see and observe what are the lone pairs. Only then can you know what will be the shape of a molecule. So there is a term used for this theory. You don't need to know the name in A-levels. This is valence shell electron pair repulsion theory. Valence shell electron pair, let me write it for you. So this is valence shell electron pair repulsion theory. In this theory, we would study that how the presence of lone pairs, and not just lone pairs, even the bond pairs, they have a special repulsive effect on the bonds and they change the angles. So we would be studying the effect of different bond pairs and lone pairs in the shape of molecules, their role in the shape of molecules. So we know we have bond pairs, just simple bonded elements, and we have lone pairs. Know one thing, that there are three types of repulsions. One is bond pair repulsion. The other is bond pair and a lone pair repulsion. And the last is lone pair repulsion. So obviously, lone pair, they cover more space. That's how we sometimes show a lone pair. When we know that a bond pair would just be a bond, a straight line, whereas a lone pair will take a cloudy shape. So it would have a repulsive effect on the other bonds, hence changing the bond angle and bond geometry. So therefore, lone pair repulsion is the most. Then it's bond pair and lone pair repulsion. And lastly, bond pair and bond pair repulsion. Even simple bonds have repulsion. So let's study various types of molecules, and we will be discussing various examples and a good number of examples so that you can understand. Let's talk about the very first type of molecules, AB2 molecules. What is A? Let's make a key first. A, B, and L. Where A is a central polyvalent atom. And when we talk about B, that's a bond pair. And L is a lone pair. So in the first type, AB2, we see there is one central atom and there are two bond pairs. And no lone pair. It is simple that they have a very easy shape and an easy geometry. Like the geometry is the shape that's linear, and the angle is obviously a linear line would have a 180-degree angle. This is something you need to memorize. They asked that in P2 and P1 for AS chemistry. So, and this would even help you later in transition elements in A2 as well, these shapes. So first of all, let's talk about a few examples. First example is beryllium chloride, BeCl2. So we can observe from here is beryllium is the central metal atom. Central atom, not metal atom, central atom. It can have various valencies. So this is A, this is B2. So in order to understand that, we need to know the valency and the electronic configuration of beryllium first. So beryllium, 4 is the atomic number. This is 1s2 and 2s2. Now, at this point, we can see that beryllium will not make any bond. Fully filled inner, we will never talk about the inner ones because it's the valence shell electron pair repulsion theory. So this is out of bounds. We will only talk about the valence shell, which is 2. So the 2s has 2 electrons. It is fully filled s orbital. So will it bond? It doesn't need bonding. It's very much stable. But when we give it energy, so remember one thing. When we have jumped to the second energy level, we not only have s, we have an empty p orbital as well. And when we give it energy, which is the process of excitation, one of the electron is going to move there. And ultimately we get, let's write it helium, because they do not matter. The inner ones, they don't matter. And then we have one here. And one electron here. So in this case, now beryllium has a valency of 2. Simply we have chlorines. Let's just make a chlorine. We don't need to know much about the other ones, the bonded ones, but let's see. Cl. Chlorine is 17. Neon. And 7 electrons in the valence shell. So chlorine will just need 1 electron for sharing. So if we have 2 chlorines, so students see that one will bond with this one and the other will bond with this one. So chlorine is balanced. But we need to look at the central atom. It's the central atom that determines the shape. So just look at this electronic configuration of beryllium. Do we see any pair of electron, any lone pair in the valence shell? Helium again, it's out of bounds. It's the inner link shell. We do not see any pair. We do not see any lone pair. Hence, this just makes AB2, 1 central atom, 2 bond pairs, no lone pair. And the shape would go on like BE, Cl, and Cl. 180-degree angle and linear. This is when we talked about single bonds. There can be cases when you will be dealing with double bonds as well. So know that a bond pair, one bond pair can mean it can either be a single bond or a double or a triple. It will just be counted as one bond pair. Let's look at the example that will make it clear for us. A very common example of carbon dioxide. We know oxygen makes 2 pairs. Oxygen needs 2 electrons since it's in the group 6. So let's talk about carbon here. Carbon is 6. The helium one is out of our bounds and we're left with this is carbon. At this point, this is the ground state. The energy is not there. Carbon can only make 2 bonds, but we know that carbon can make 4 bonds. What will happen? This is the ground state. And when we make the excited state, this electron will move to this one and ultimately we get four valence, four single electrons ready to be bonded. So what will happen? We have two oxygens, one will bond with this one and one will bond with this one. And at the end, it's done. Remember, even in the above example, we know that chlorine does have 3 lone pairs each. These ones do not matter in the shapes. Only the lone pairs of the central atom, they matter. So again, the central metal is carbon, no lone pair again. So this would be COO, another linear shape. So as I said, even the double bond is regarded as one bond pair. Let's take another example of hydrogen cyanide. Carbon is again there with 4 bonds. So H, C, N, linear shape. That is simply AB2. Let's talk about the other type, AB3. AB3 has 2 different types. One is simply AB3, 3 bond pairs, no lone pairs. So when we talk about this example, initially it's a very basic example. Let's talk about aluminum. It's in group 3. So aluminum will have this electronic configuration. But again, we excite it and ultimately this electron comes here. And if we have a compound like a common one, an important one, AlCl3, aluminum chloride, each will be bonded with one Cl because Cl just needs one electron. So do we see a lone pair here in aluminum? Not at all. There is no lone pair. So that is when we have A, the central metal, central atom, and 3 bonds. What will be the shape? I hope you have fans on your ceiling. Just look at the fan. That's the shape. So the shape, we name it as the geometry would be trigonal planar, and angle would be 120 degree. So how would we make the shape? Al, 1 chlorine here, 1 chlorine here, 1 chlorine here, Cl, Cl and Cl. And we know that the angle is 120. 3 120s make 360, so that's a circle. So this is a planar molecule. There are no, there are no lone pairs. So let's look at the shape here. We have markers to support our cause. Linear was simply this way. So could we make a 3 bonded one this way? It could have been made this way. But as I said, we do not have lone pairs. We just have bond pairs. So even they have slight repulsion. And the repulsion of bond pairs will lead the angle to become like a fan. And it's planar. It's just one plane and 120. This is the shape of AlCl3. And we call it trigonal planar. It's a triangle. But the name in chemistry is trigonal planar. There are various examples. Bf3, boron has just a similar electronic configuration as of aluminum group 3. So B, F3. Time to hate sulfur. In this topic, sulfur is going to be the most confusing one, students. Let me show you how. Sulfur's electronic configuration: 16, neon, it's in group 6. Group 6, so 6 valence electrons. That's what we know about sulfur. But then we know that this is a 3s, 3p. So, if I tell you we have a compound named sulfur trioxide, so oxygen will always make 2 bonds. So what should be the valency of sulfur? 6. But we only see 2 valence electrons. How will that happen? What will we do? Do we see any other vacant orbital to be filled with? Yes, we have a subshell. When we jump into third energy level, students, we have an empty d subshell, because third energy level has a d. So that would be 3d. If I just excite this electron, we still have a valency of 4. What will we do? We will further excite this one as well. Excitation is jumping from a lower energy orbital to a higher energy. And we know S has a lower energy, P has a higher, D has a further higher one. So now we have 6 electrons that are desperate to be shared. Oxygen, oxygen, oxygen. Complete valency. Do we see any lone pairs in this sulfur's valence shell? We do not talk about the inner link shells, only the valence shells. No. So the shape would be sulfur trioxide. Again, a trigonal planar, but sulfur is like a chameleon. It will change its shapes, it will change its colors. It's going to give you a tough time. There are many shapes that sulfur can make. That's why we call it a polyvalent. It can have various valencies. But more importantly, there are 2 ions, polyatomic ions, that are very important: carbonate and nitrate. Carbon, we know that carbon can have a valency of 4. In excited state, that's how carbon looks like. So we can only make 4 bonds, but we have 3 oxygens. So one oxygen will make a double bond. One will make a single, the other will make a single, negative, negative. So carbonate ion, the carbonate ion is also trigonal planar in shape. Nitrate ion. So nitrogen exists this way. What do we see? Just 3 electrons. But in a nitrate ion, there is going to be excitation. And this electron will go here to the d orbital, d subshell. Now, what happens here? Nitrogen has now a valency of 5. So N, 4 valencies are filled and 1 oxygen minus. So even nitrate ion has a trigonal planar shape. This was AB3's first type, just AB3. Then we have another example of AB2L1. Let's welcome a lone pair now. In this case, we have 1 polyvalent atom, 2 bond pairs, and 1 lone pair. And as I said, you're going to hate sulfur. Let's talk about sulfur dioxide. But initially, let me tell you, this shape, this has a bent, or it's V-shaped. The geometry is bent or V-shaped, And the angle, here the angle was 120, right? It would be less than 120. So 117 to 119, it's not fixed. Shape, angle. So let's talk about sulfur dioxide. We are welcoming a lone pair here. Again, let's see. We had sulfur somewhere. Okay, let's make our own sulfur again. Sulfur has 6 electrons, and this sulfur can only bond with 2. But SO2, remember, O will make 2 bonds. There are no charges. So we need to excite at least one of them. So this one will be excited. Only this one will. And we get 4 lone electrons. So oxygen, oxygen. Because oxygen has an electronic configuration of this sort. So it needs 2 electrons to share, to make a covalent bond. So we have electrons valencies filled, but in the valence shell, a lone pair is also there. So what happens, students? AB3 will have bonding in this way. AB3 will always have a bonding in this way. So this is 120, 120, 120. But now this bond is removed. We've just got a lone pair here. And as I said, lone pair will be more repulsive. So if there's a cloud of lone pair, the angle will be compressed. Lone pair is going to have a repulsive force on the angle and it will go less than 120. So initially it was 120, but due to lone pair, it got decreased a little. So that is a V shape or a bent shape. So let's see. Lone pair, you draw a lone pair and then two oxygens. So that's a sulfur dioxide. Sulfur dioxide was 120, simply a trigonal planar. This is bent. This can be 119, little lesser. And that was because of the lone pairs cloud. Similarly, tin chloride, SnCl2, similarly bent shape. That's it. Now, one of the most important one in chemistry, AB4. Why is it one of the most important? Because this one is going to deal with carbon mainly. And when we talk about carbon, that's organic chemistry. So AB4, the first type is simply AB4. 4 bond pairs, no lone pairs. So let's just talk about it. The most important example is that of methane, CH4. Carbon will make 4 bonds in its excited state. And we have 1 hydrogen each. We will be further studying it in hybridization. That changes things a little more. But how will the shapes be like? So, carbon is just making 4 bonds. We normally make methane this way. Just right angle to each other. But let's get realistic now. Let's say, for instance, this is the right angle shape. It doesn't look right angled, I'm sorry. But as I said, we don't have lone pairs as the figure says, as the electronic configuration says. But even the bond pairs have repulsion. They are not satisfied with a 90-degree angle. So they would be repulsing each other more. But this cannot get closer. 90 is not a satisfactory angle. So what will happen? This time, students, we are jumping onto a 3D shape because planar was not enough. Bent was planar, linear was planar, trigonal, planar was planar. Now we are jumping onto a shape called tetrahedral. Let me try to make it. I'm mostly successful in this, but it happens. So if I say this is the shape, obviously my fingers can't do the justice here. The struggle. This is taking a lot of time. Now, I can do it with two hands. This would be somewhat like this. A 3D shape. Whichever angle you take, it's going to have the same shape, the same angle. I am successful now. Hooray. So shape, angle. And the angle would be not like this, but all the carbon bonds, all the bonds in AB4 would have a similar angle. And that would be, the shape would be tetrahedral. And the angle would be 109.5, or just, you can write 109 degree. That's the angle. All the bonds are similarly distanced with this angle. So we will not make carbon dioxide, methane this way. We would rather make a 3D shape with a dot and wedge model. So this is a wedge, this is a dot. Wedge means towards us, and like it's coming towards us. And dotted is going out of the plane. So wedge and dot both are going out of the plane. So we cannot do that in the paper. Obviously, we cannot tear our paper apart. So this is how you make methane. CH4, no lone pair. That's important, students. But as I said, sulfur. Let's talk about sulfur again. A very famous ion, sulfate ion. For sulfate ion, sulfur will take the similar electronic configuration that it had here. No lone pair. So what would happen? Two oxygens will be there with double bonds, as sulfur can make 1, 2, 3, 4, 5, 6 bonds now. One will be dot with a negative charge, and the other will be a wedge with a negative charge. This is a tetrahedral shape, 109 angle. And likewise, another important ion, ammonium. So we will be talking about ammonia first, then we'll talk about ammonium. Let's talk about ammonia first. And that would be our next type, AB3L1, 3 bonds, 1 lone pair. And ammonia comes first, NH3. So what would happen? Nitrogen exists this way. And we just need to link 3 hydrogens. We do not need to further excite it. It's stable. It's perfect in its ground state. But we see a lone pair. So this lone pair will change a lot. So let's look at the shape again. AB4 is tetrahedral, supposedly. So this is AB4. Oh, that's a perfect shape this time, finally. But this time, NH3 So there are 3 bonds and 1 lone pair. So we take it out. There is a lone pair here, and it's going to put its repulsive forces, and it goes down. It becomes this way. The angle 109 has reduced. And let's talk about Egypt here. What shape do you see here? This shape, pyramid. So now, students, let's try to make a structure. We have nitrogen with a lone pair. So the shape is, because there is 1 lone pair, 3 bond pairs. So the shape would be trigonal pyramidal. And the angle, it was previously 109. Now it would be reduced to 107 degree. And there are further examples. For instance, PCl3. PCl phosphorus has the same electronic configuration as that of nitrogen. 5 electrons in the outermost. So it would do the same thing. 1 lone pair, Cl, Cl, Cl. So PCl3 would also have it in this similar way. Now let's talk about the other example, the other type. My apologies. Ab2L2. Don't worry, this is the last tricky one. The next two are very basic. So you do not need to worry. So 2 bond pairs, 2 lone pairs. And your favorite, your very favorite, sulfur comes again. So sulfur, but this is a basic one. Oh, not argon, it's neon. Oh, I forgot to mention the name of the example, hydrogen sulfide. Hydrogen sulfide. So, sulfur just needs 2 hydrogens, so both the lone pairs will stay. So S, lone pair. Let's see what happens. It was this way and this way. This got removed, lone pairs. V shape. Again. So, this one is also V-shaped or bent. And that reminds me, we still have to do the ammonium example, but we would do it after the next example, one of the most important ones. Whenever I'm teaching, students normally ask, so why is water not an Ab2 type? H2O. And that is only because of oxygen. Oxygen is the central atom. So hydrogen needs 1 bonds, 1, 1, H, H. So we are left with 2 lone pairs again. 2 bond pairs, 2 lone pairs. What would happen? O. Even my O-level students always ask me, sir, why do you make water this way? And that's because of my practice. So water also has a bent shape, and this bent shape will further help you in bonding, hydrogen bonding, and the shape of the ice. So this shape is very important. So now, before we talk about AB5 and AB6, there are no further types, just AB5, just AB6. They are basic, they are simple. Let's talk about ammonium. We saw ammonia. Students know one thing. In the exam, they can give you a hydrazine molecule. And they can shape it this way. And even if I remove the bond pairs, lone pairs, let's say there are no lone pairs. they give you this shape. It looks like a 90-degree angle. But know one thing. This is nitrogen. And it's making 1, 2, 3 bonds. So when nitrogen is making 3 bonds, there is always a lone pair left. So if the lone pair is left, the angle here would also be 107. Not 120, not anything else. It's making 3 bonds, 1 pair is left. So it's also 107. This is a common exam question. Not just an example, an exam question. Ammonium. How does ammonium form? We have ammonia. And you must have seen it in my video. You can see that video, the lecture of dative covalent bonds. That nitrogen shares its lone pair to a hydrogen ion, H plus ion. That's dative covalent bond. H plus ion has no electron. It can gain 2 electrons. So that's what happens. But when the lone pair goes there is no lone pair left. Lone pair has become a part of bonding. So this also becomes an AB4 type because lone pair is here. It looks like a bond. It's not impacting the shape. So ammonium will also have a shape of tetrahedral. Now the last 2 examples, last 2 types, very basic, very simple. Just do not worry about them. And they are AB5. For that, let's call our friend phosphorus back. So phosphorus here made PCl3. Remember, phosphorus also makes pH3, pH5. And similarly, phosphorus will also make PCl5. So it needs 5 bonds. What will happen? One is excited and ultimately 5 bonds. No lone pair, no further example. There's only one PCl5. That's this. Now let's talk about the shape. That's a crazy one. Because they do repel. It's not that they're going to make 5 bonds this way. Just random star shape. No. 3 of them will make a trigonal planar shape. This way. 3 of them. You have 5. And one will come at the bottom. The other will come at the top. So this is the shape. And if you see, there is a top going this way, and this way. There is a pyramid at the top, pyramid at the base. Let me try to draw it. They never make you draw it in the exam. So this top is going 3 ways. So I hope this looks like a pyramid to you, and the same will happen at the base. This is, as the name goes, trigonal bipyramidal. But the angles are still not easy here. They're easy. You just need to memorize if you can. What is the angle here? It's the same fan, trigonal, 120. But what are the angles now? 90, 90, 90. And the base one, 90. So the angles that we have in trigonal bipyramidal are 90 degree and 120 degree. And you would be delighted to know. That's it. That's all about AB5. Now the last, AB6. And let's call back our own friend, sulfur. Sulfur in the 6 valence state. Let's just copy it from here. In the other cases, sulfur was making double bond, triple bond, double bonds, not triple bonds. So it was a different bond. But here it's making 6. SF6, SCl6, 1, 2, 3, 4, 5, 6. The same excitation. This time, there's a lot of repulsion. Finally, right angle comes here. So there would be a right angle. Just like in bipyramidal, we had a 120 angle here. This time we'll have a 120, 90 angle here, 90 degree angle here, and 90 on the top, 90 on the bottom. So it's 90 from every direction. 90 from every direction. We just show it this way. That these are 90 to each other. And then this is also 90 to this one. When we all connect the dots, the shape is, it doesn't look like that because no, I can't draw it that way, but it looks somewhat like that. Yeah, it does look like that. It has 8 faces now. 8 faces. So the shape is octahedral and the angle is 90 degree. So that's all that we know about the shapes and angles. That's all that you need to memorize. That's an important exam question. We will be discussing the past paper questions. We will be discussing hybridization. Orbital hybridization is very important. And it is related to this one. So thank you so much for being here with me. Allah Hafiz.